All right, we're on page 1 of notes 15 of Calc AB, and what we're going to be talking about is taking the limits of Riemann sums, but I mean, I don't know if we really know what that means. What that means is we're going to use n rectangles. Like in the previous set of notes, we were using like 5 rectangles. Well, no, we were mostly using even numbers like 2 or 4. What here we want to do is we want to use n rectangles, come up with like a generalization. And then after we have our generalization, we want to see what happens if n goes to infinity. As we increase the number of rectangles, we get a better and better estimate. If we use an infinite number of rectangles, we will get the exact value of our definite integral. So that's what we want to do. To do that, we need to know some stuff about summations. And so what we're going to do is start off by just writing these using sigma notation, and then we'll go from there. So because there are a bunch of formulas that you may or may not have memorized at this point, probably in algebra 2, maybe in a pre-calc class, not in my pre-calc class, but algebra 2 potentially. Those all start at 1, so we're going to start at 1. So this is a preemptive strike so that we know what to do when we get there. So here, I'm going to say that this is, all right, so if this corresponds to like 1 and then 2, 3, 4, 5, 6, 7, 8th term, I'm just going to say this is the sum from I equals 1 to 8 of I. And that's it. All we want to do is write them using sigma notation. And we did. So, I mean, that's totally fine. What about here? So I want this to be when I is 1, and then 2, 3, 4, 5, 6, 7. So we're going to go from 1 to 7 because there are 7 terms here. So I equals 1 to 7. Now what am I going to do? So the first term, this is when I is 1. So I'm just going to add 8 to it. I'm going to say this is I plus 8. And this should work for me. There's an infinite number of ways that you can write these. Like, you don't have to write this. I definitely want to start at 1. And then it's like, you know, so 9 is equal to what? And I'm saying it's I plus 8. You could probably find other formulas that make it work, but you have to make it work for everything. So when I is equal to 2, this is 2 plus 8, 3 plus 8, 4, 5, 6, 7 plus 8. Totally works. These all represent numbers. The next one is actually different. This is a polynomial. So what we're going to do is we're going to write a summation that's equivalent to a polynomial. Later in life, when you get to Calc 2, you're going to do that like a ton. And so this is kind of interesting. So again, we're going to start with I equals 1. And then, so this is when I is 1, 2, 3, 4, 5, 6. So we got to go from 1 to 6. And we're just like pattern finding here. Coefficient is always 1, 1, 1, 1. So I think what I can do is just x to the I minus 1. And so when I is equal to 1, I get x to the 0. When I is equal to 2, I get x to the 2 minus 1, so x to the first. When I is equal to 3, I get x to the 3 minus 1, which is 2. And then finally, when I is equal to 6, I get x to the 6 minus 1, which is 5. So this is working. So this is a really weird way of writing a polynomial. You can type this, by the way, into your calculator, and it will do it. It'll expand it for you, and it'll show you this. I think it'll probably put it in the other order because the calculator prefers you know, standard form or whatever, like highest to lowest power, but still, it works. All right, so this one, pretty similar, I think. So often what you want to do, just like figure out what's going on, right? So this is like 2 to the first, x to the, let's say 1 plus 1, plus 2 to the second, x to the 2 plus 1, plus 2 cubed, x to the 3 plus 1. So you might be wondering, like, what do I do if there is no pattern? Which is a great question. You just won't be asked to do it. Like, there's going to be a pattern, and you're going to find it. So, like, that's not something you really need to worry about. All right, so I think we're going from 2 to 4, no, from 1 to 4, rather. I think we have a 2 to the I, and then an x to the I plus 1. So when you get up to, when I is equal to 2, for example, you get 2 squared and then x cubed. And this is when I is equal to 2 because it's the second term that you're getting. So that works. All right. Now these are getting a little weirder. They're going to start being function notation, but that's not really a problem. We just have to keep working on it, right? So look for the thing that's changing. It's x sub 3, 4, 5, 6, 7, 8. So that's what's changing. So I'm going to say that we're adding up from 1 to, so from 1 to what? Well, what do we think we're doing? I think we're doing g of x sub, so when I is 1, I get 3, so it looks like I plus 2. Okay, so where should we stop? Well, I'm saying that this is g of x sub 6 plus 2, right? So 8 is equal to I plus 2. What is I equal to? I is equal to 6. So we're going from 1 to 6. So I think that'll do it for us. That one's weird, but not a problem, just different. So incidentally, this last one, if you wanted to, you could kind of start representing in picture form. I mean, you could probably do this with all of them, like if you're good enough. So let's say this is like g of x, right? And so you have, I'm gonna break this into 8. So what I did there, if you were following, is I did this, then I broke that in half. And then, so I have 2 parts now, and I broke this in half and this in half. And then I broke each of these in half, and that gives you 8. So powers of 2 are pretty like straightforward to do that for. So this is like x8, 7, x6, 5, x4, 3, x2, x1, and x0. So what we're sort of doing here, and just it depends on how you look at it. Let's say we were doing a right Riemann sum. If we were doing a right Riemann sum, so each of these is like 1 times g of x3, 1 g of x4. I don't know, actually, let's say that they're 1 apart. This is falling apart. But anyway, let's say that they're 1 apart. You can kind of view it as this, right? As long as they all differ by 1, which, like, why not? Right? Let's say delta x is always 1. If delta x is always 1, then actually if we knew what x2 was, we would know what all of them are. But this could represent a right Riemann sum for g of x starting at x2, right? So we're really going from x2. So this could be a right sum for the integral from x2 to x8 of g of x dx. And that's what we want to do. We want to like look at these and be like, can we figure out if these are a definite integral? So here, for example, let's first just write a thing. So they're all 3. So we'll do the sum I equals 1. So it's going to be 3 times h of x sub. So we're starting at 1. So I'm going to say I plus 3. And then if I plus 3 is equal to 8, then I must be 5. So we go up to 5. So writing that part's not that bad. I'm going to say each of these could be a rectangle with a base of 3 and then a height of h of whatever you're plugging in. So here we would have, oh no. So I kind of encourage you to do this. Like try to think graphically. It takes a little practice, but I think you'll be okay. So let's say that this is, where are we starting? At 4. I'm just going to start at x4. x4, 5, 6, 7, x8. And then each of these is 3, right? So that's like our base. And then what we're doing is, oh, so you know what? Maybe, I like to do a right Riemann sum. So what I'm going to do is I'm going to say, move that a little bit. We'll say this is x3. That's 3. So the first rectangle we're going to make is at x4. Let's give it a function. Right Riemann sum. So they're all 3 apart, and we're doing a right Riemann sum, and it works. Try to think of your summations as Riemann sums. It's like, it's maybe not the most natural thing in the world, but you get used to it. All right, let's take a look at this one. We're going from 1 to 5. This one's might be the most straightforward so far. Well, maybe. So we're definitely going from 1 to 5. I think it's f of x sub I delta x. This one very much feels to me like a rectangle, right? So rectangle, the base is delta x, and the height is f of x sub I. And then our question will just be like, what's x sub I? Like, what are we going to plug in? Well, we'll work that out eventually. But I think you can definitely interpret this that way. So that's pretty good. What do we have going on here? So this is like pi times something squared. I'm trying to highlight, I don't know what I'm highlighting here. Something squared, something squared. So it's pi something squared. What do we know that's pi something squared? Well, the area of a circle is pi r squared. So maybe these are like circles. But what if we said, for various reasons, what if we said there was a 1 in each of these multiplications? 1 times this, 1 times this, 1 times this, etc. I guess I'm committed. 1 times all, there's so many. 1 times this. What if we said that? So now we have pi r squared times 1. These could all be cylinders, right? Pi r squared h. We have a cylinder. It would be pi r squared h. If h is 1, and then r is f of x sub I, it looks to me like we're just adding up a bunch of cylinders. So that's like kind of a weird concept, unless if you took analysis, you know that we frequently add up cylinders to approximate volume. So what are we going? 1 to 6. I'm going to say it's pi times 1 times f of x sub I squared. So we're just making a lot of cylinders, we're adding them up. I think the next one looks like an even more generic form of that. And so I'm going to do that. So I'm going to say it's a cylinder again. Now, part of the advantage that I have is that I like recognize these things, and you will too very quickly. I'm going to say h is delta x, r is f of x sub I, and we just don't know what f of x sub I is. We don't know what x sub I is. We don't know what f of x is, but we're pretty sure we're just making cylinders and adding them up, and that would approximate the volume when you rotate something. So from 1 to 4 of pi f of xi squared delta pi r squared h. So I put it in the order pi r squared h. This last one I did pi h r squared. It's kind of weird, but you got to multiply by 1 eventually. I think that would work. So, I mean, what you're essentially doing there is you have your axis, you have this. Let's say you have x0, x1, x2, x3, and x4. And then these will be delta x's. Delta x, oh wait, that's not a delta x. I mean, it could be a delta x, but we don't need it. Ah, too much. Okay, so then you make a rectangle. So I don't know why I'm trying to make this one particularly good, but I am. It's like it works, and then when it gets really close, it wants to like grab onto something, and it just doesn't work. So this, and then this. So it's worth thinking about. That's why I'm spending a little bit of time on this, trying to like make it. Okay, yeah, you're definitely not an oval or an ellipse. Whatever. Okay, that. Then we're going to take each of those and rotate them. And so like this is f of x4. This height is like f of x3. This height is f of x2. Those are going to be the radius of each of the cylinders that you get. So you end up with a cylinder where this is delta x, and then this is f of x sub I. So it's pi r squared h. That's what you get. So the reason we want to start at 1, we're basically done, is that we're going to use those formulas that you maybe learned in Algebra 2. I learned them in Algebra 2. You may actually never have learned them. You're going to see them in a second. And we're going to write our summations, and then we're going to be able to work with them. So this was just practice on writing summations. I'm going to end this here. I will be back in the next video to do some more. So I will see you there.